So as mentioned, difference between outer hair cell and the inner hair cell. I hope that it is clear. Outer hair cell responsible for hearing sensitivity, improving sound clarity and frequency resolution. Inner hair cell initiating neurotransmitter action and initiating action potential. Outer hair cell mainly station for relay station for feedback from CNS. It is receiving higher number of efferent neurons than inner hair cells, while inner hair cell synapse mainly with afferent. So down-up propagation is responsibility of inner hair cell, up-down feedback is responsibility of outer hair cell. Outer hair cell constitute cochlear amplifier. Main purpose of outer hair cell is not to stimulate auditory nerve, but to change mechanical properties of organ of Corti to be transducted to inner hair cells. In anatomy, I have said that outer hair cell have contractile action, while inner hair cell not. Force of vibration of basilar membrane depend on outer hair cells. So main purpose of outer hair cell is to change mechanical properties of organ of Corti, affect transduction in inner hair cells. As here, outer hair cell, stereocilia emptied in tectorial membrane. While inner hair cell not emptied in tectorial membrane. There is a space between inner hair cell stereocilia and the tectorial membrane. Fluid space. While in outer hair cell, it is directly embedded into tectorial membrane. So it is responsible for intensity of vibration of basilar membrane. So act as amplifier by enforcing the vibration of basilar membrane for soft sound and decreasing vibration to loud sound. Something like compression action in hearing aid, enhancing soft sound and protect against harmful effect of loud sound. Stimulation of outer hair cell causing inward movement of potassium. This contract motor protein in the cell wall and shorten cell. So with transduction, depolarization of cells causing ion channel to open, inward movement of potassium from surrounding fluid to inside the cells, contracting protein cells in these cells or in outer hair cell, causing shortening of cells. This shortening of cells lead to inward movement of tectorial membrane. Pulling reticular lamina to basilar membrane and cause stereocilia of inner hair cell to bend more. With soft sound, contraction of actin protein in outer hair cell, more vibration of basilar membrane, more transduction of inner hair cells. This amplification action of outer hair cell causing about 50 dB at low and medium sound. Again, of outer hair cells at low or soft sound is about 50 dB by increasing its contraction and increasing vibration force of basilar membrane. Figure of outer hair cells. Inner hair cell, as mentioned in anatomy, was flask shape, while cylindrical shape is outer hair cells. When hair or stereocilia on cells are bent toward tallest stereocilium, depolarization, more activity in nerve, while bending away from it, hyperpolarization and decreasing activity in auditory nerve. This is tuning curve according to frequency. When outer hair cell damage, instead of sharpening, this is tuning of frequency. This is the best frequency at which this part of basilar membrane vibrate. Tuning of basilar membrane, frequency analysis. And at each point of basilar membrane, it is specific for certain frequency by analyzing sound entering or speech into its main frequency component. and each part of basilar membrane will vibrate optimally at certain frequency. And this is fine-tuning curve of that frequency. When outer hair cell damaged, vibration of basilar membrane will be dome-like this figure. So it is broadening and no frequency resolution, no selectivity. So patient will complain from decreased ability to discriminate sound. He can hear, but he cannot discriminate. With outer hair cell damage, instead of sharp tip region, this tip region, frequency selectivity is broadened. Reduced frequency discrimination. And this is the main complaint of patient with high frequency hearing loss or steep sloping curve. He can hear, but he cannot discriminate. This is top view of stereocilia on hair cells. Stereocilia of outer hair cell beside each other forming W shape or V shape, while stereocilia of inner hair cell forming U shape. And this figure, we can see cross-link between stereocilia. Another figure of organ of Corti. On top of hair cell sit tectorial membrane, which is attached only along its inner edge. Inner edge of tectorial membrane, upper edge is freely floating into endolymph, while inner edge is attached to outer hair cells. Here, there is space between inner hair cell and tectorial membrane. Here, stereocilia on inner hair cell didn't reach or don't reach inner edge of tectorial membrane, while here, stereocilia of outer hair cell reaching and emptied into tectorial membrane. With its contraction by soft sound, moving tectorial membrane downward, causing its touching of stereocilia of inner hair cell and starting of depolarization and transduction. On top of hair cell sit tectorial membrane, which is attached only along its inner edge. Stereocilia of outer hair cell emptied in tectorial membrane, but those of inner hair cell are moved by movement of fluid in space between hair cell and tectorial membrane. Another view, top view of stereocilia on outer hair cell, and this is 3 rows of outer hair cell, and this is single row of inner hair cell. Here in this figure, outer hair cell are damaged due to any disease, either ototoxic drug or heredofamilial. There is loss of outer hair cells, and some of inner hair cell are lost too. So tectorial membrane and the basilar membrane lost outer hair cell function of frequency selectivity, frequency resolution, and amplification process. Basilar membrane. Basilar membrane has 2 structural properties that determine the way it responds to sound. Here is the base. This is oval window, which vibrate by movement of stapes, inward movement of stapes, moving fluid in scala vestibuli. Basilar membrane at the base is narrower than basilar membrane dimension at the apex. So it is narrow at base and wide at apex. Stiff at base and loose or more flexible at apex. يبقى basilar membrane narrow and stiff at base, broad and flexible at apex. This causes high frequency to mainly be processed at base and low frequency mainly processed at apex, like strings of musical instrument. When a string is when we tightening this string, we get the high frequency sound or thin sound, thin pitched. When a string not tightened, the sound will be harsh or not thin sound. Pitch will be harsh. Basilar membrane mechanical frequency analysis separating incoming sound signal into its main frequency component processed at different location along length of cochlea. High frequency processed at base and low frequency processed at apex. As here, basal membrane is wide and flexible, while here it is tightened and stiff and narrow. Transduction mechanism. Sound-rich cochlear duct stimulating organ of Corti, stimulating inner hair cells, act as pure receptor that transmits signal to its nerve, or cochlear nerve. Outer hair cell act as sensory and motor elements that elongate and contract by planned action of filament as actin. They are crowned by stereocilia, each consists of actin core. Their tips are linked by tip link. This is actin core. This is tip link between stereocilia and inside each stereocilium actin core, which contract to elongate and shorten it. Bending toward the tallest stereocilia will cause depolarization, causing traction on this tip link, opening of ion channel, indrawing of potassium, entering of potassium in high amount, causing opening of calcium channel at the base of stereocilia, at the base of cell, I'm sorry, at the base of cell. Entering of calcium lead to rupture of neurotransmitter vesicles and release of neurotransmitter, that beginning of transduction in nerve. يبقى bending of stereocilia toward the tallest stereocilium, causing potassium channel to open, membrane to depolarize, opening of calcium channels and inflow of calcium, and a rupture of synaptic vesicle, release of neurotransmitter. This is mechanism of transduction. Repolarization, when sound is processed and transduction done, cell shall return to its resting potential by repolarization, by release of potassium. Now potassium entering outer hair cells, then release of potassium through potassium channel into supporting cells, to stria vascularis through gap junction formed by connexin. So loss of connexin leading to hearing loss due to disturbance of ion change mechanism. Then back to endolymph. From outer hair, from endolymph, from surrounding fluid to inner hair cells, to outer hair cell, to supporting cells, to stria vascularis, then back to endolymph. And cell return to its resting potential. What's binaural squelch? Ability, as we said, water filter lead to getting of clear product, which is clear water. Our system leading to filtration of sound to get clear message and clear speech, that we can hear speech clearly with high resolution. So higher centers, mainly in brainstem, leading to filtering of surrounding noise, which is called binaural squelch. Ability to suppress background noise and attend to specific auditory signal, enhancing wanted signal and suppressing another noise. Auditory nervous system help in noisy situation as long as there is functional input from both ears. Auditory system and the brain combine information from both ears, that there is better central representation than would be with only one ear. Squelch effect takes advantage of spatial separation of signal source and the noise source. Difference in time and intensity, as mentioned before, there is interoral time difference, interoral intensity difference. Sound coming from right side, so right ear hearing it louder, and left ear hearing it less louder. So there is difference in intensity between both ears, in intensity of sound and in time arrival of sound. Brainstem can analyze this fine-tuning criteria to detect source of sound and to enhance wanted sound and suppress background noise. Squelch effect takes advantage of spatial separation and timing separation of signal by difference in time and intensity between both ears, interoral time difference and interoral intensity difference. Speech recognition in such noisy environment is even harder for a person with sensory neural hearing loss. This is nervous pathway after sound processed in peripheral ear, then pass through depolarization done in hair cells and beginning of transduction through nerve in its nerve, stimulation of nerve leading to stimulation of cochlear nuclei in brainstem, then ventral cochlear nucleus and dorsal cochlear nucleus, then superior olivary complex, which is abbreviated as SLIM, superior olivary complex, to lateral lemniscus, and to inferior colliculus in thalamus, and then to medial geniculate body, and at higher centers in auditory cortex. This is summary of auditory pathway. So after its nerve transduction begin in its nerve after depolarization of cells, spiral ganglia stimulated, spiral ganglia in Rosenthal canal as mentioned in anatomy, in wall of medullus, to auditory nerve to brainstem, dorsal and ventral cochlear nuclei in brainstem, superior olivary complex, get information from both cochlear nuclei, here binaural response properties. Superior olivary complex receive information from both cochlea or from both sides. So he can comparison is done between both sides and determine interoral time difference and interoral intensity difference. Medial geniculate body, auditory thalamic relay nucleus, acoustic radiation fiber from medial geniculate body to A1 auditory cortex center, from A1 auditory cortex center to Brodmann area 41 and superior surface of temporal lobe, and then to secondary auditory cortices, Renix area. This is auditory pathway. Cochleovestibular nerve to cochlear nuclei to inferior colliculus, medial geniculate body, and auditory cortices. Tonotopic map of sound frequency. As said, our system from periphery up to central analyze sound into its main frequency component, starting from tympanic membrane, which respond differently to different frequency. Different part of tympanic membrane respond to specific frequencies, and to basilar membrane, which more analysis of sound, then through auditory nerve to brainstem, and then to higher centers. Map of sound frequency from basilar membrane. In cochlea is preserved, there are tonotopic map on basilar membrane, medial geniculate nucleus, auditory cortices, and within each of the nerve relay nuclei. So tonotopic representation of sound is preserved from down peripheral system up to higher centers. This is auditory cortices and showing that each part of auditory cortex respond to specific frequency with preservation of tonotopic organization. The axons in the main auditory pathway are heavily myelinated. Fast transmission means that auditory pathway are easily visualized in section. Also means that you can measure activity from scalp, which is basis of ABR. There are two important reflex loop from superior olivary complex. From superior olivary complex, two pathways emerge. One back to cochlea, up-down feedback, allow loud sound to modify vibration of basilar membrane, which was mentioned efferent synapse with outer hair cells coming from superior olivary complex. And acoustic reflex negative feedback to middle ear allow loud sound to decrease input of sound into cochlea, causing contraction of stapedius muscle and preservation of cochlea and protect it against loud sound, harmful effect of loud sound. So with this feedback loop, if disturbed, hyperacusis is noted and patient will complain from sensitivity to loud sound. This is the whole mechanism. Sound move tympanic membrane, vibration of ossicle, oval window. Thank you, Dr. Shaibani. Sure. I'll upload the record. Thank you. Thank you for attendance. Sound wave move tympanic membrane, then ossicles, then oval window vibrate, vibration of fluid of cochlea, response in sensory neurons, causing a hair cell to depolarize, then transduction in cochlear nerve will start to up to cochlear nuclei, superior olivary complex, inferior colliculus, medial genicular body, and primary auditory cortex. Example of abnormality, as mentioned, the normal pathway and normal anatomical parts of ear. Any abnormal part of ear, either pathologically or congenitally, there will be disturbance of its function and hence complaint of patient as congenital anomaly in external auditory canal or auricle, causing conductive hearing loss. Congenital anomaly or pathology in middle ear either, or tympanic membrane, or stapes, or incudostapedial junction, or stapes with oval window, causing conductive hearing loss. A congenital anomaly or pathology in cochlea causing sensory neural hearing loss. So according to function of each part of pathway or system will be the complaint of patient if this part is pathologically affected. Thank you.